Hey guys, Mr. Wood back for another lesson here in Chapter 6, continuing on in Chapter 6, but we need jokes. So here we go. What did the judge say when the skunk walked in the courtroom? Odor in the court. See, not order in the court, odor in the court. Lexi and Ryan like that. Okay, here's my other one. I like this one too. What happens when frogs park illegally? They get towed. Those were two good ones. I don't care what you guys say. Okay, so here we are. We're going to do the next, I don't know, almost 20 minutes, just continuing on in Chapter 16. So we talked about delta E, and we talked about work and how those work. And that was kind of an introduction into stuff that we're going to be moving into. So we talked about this. Energy is measured. Energy, heat is a form of energy, is measured in joules, kilojoules, calories. Remember, a large C calorie is the same thing as a kilocalorie. Remember, temperature is measured in Kelvin, Celsius, Fahrenheit. So these are different things. Okay, so and we went through this in class. Okay, and we've done this problem, and again on the test on Chapter 6. Hopefully, right before Thanksgiving, there'll be a problem like this or this. And here's where work comes in, and we talked about the units and what's on your formula sheet, and we did those problems. So make sure you're good with that. You'll see that on quiz or test. Okay. And then we did this problem, and that's where we stopped. So again, not a major point in the chapter, but definitely being able to do those problems with delta E, Q, and W. Okay, and this is, I think, where we left off. And so here, enthalpy, and this is actually on the formula sheet again, and we're going to come back to this later in the chapter. I know you can hardly see me, but if you look on the back, on the lower left-hand side, there it is, which it says right there at the top, that the delta H is equal to the H of the products minus the H of the reactants. And we've already talked about an exothermic reaction, where heat is lost by the system, the surroundings gain heat, so the temperature goes up, the delta H is negative. An endothermic reaction, a reaction that absorbs heat from the surroundings, so the temperature goes down. Often the surroundings immediately around the reaction will become cold, the delta H will be positive. Okay, and today we're going to get into some of these different ways to solve for delta H. The first one we're going to look at is stoichiometry. We might get into calorimetry a little bit. Hess's law, and then from a table, and then the bond energy things we'll do in Chapter 8. Sometimes there's stoichiometry along with some of these others, a combination of these. Okay, so here's the first one, stoichiometry. And actually, to do this problem, I need to give you the equation, which I'm going to do. So we're going to come back and look at this one here in a second. So here, we're not going to use this data to do that, but here's a physical change, and this is an endothermic reaction, and I can tell that. And there's two ways to write it. You can see the two ways to write it. And in this case, energy is going into the system. H2OS means solid, ice. Just like the past couple of days, we've had a lot of snow and ice, but you put energy in and it melts. And the other way to write it, indicating that in that case, delta H is a positive. So the system is higher in energy, an endothermic reaction. Now here's what I'm going to use to go back and answer that problem. But this is methane. This is the reaction that occurs when we light a Bunsen burner. Okay, so I'm going to do this problem here on the chalkboard. Okay, there we go. Sorry about that. I always have technical problems. Okay, so the first one, the physical change reaction. So what we did is we wrote out, we had 6.01 kilojoules plus H2O solid makes H2O liquid. See, this is an endothermic reaction. because the energy is on the left side. The other way to write that is the H2O solid makes H2O liquid. And then I include delta H, and most people would write in it's positive. They would write in it's positive because it is endothermic. Okay, the other reaction we're going to use to do that problem. So we get off CO2 and 2 waters. And one way to write it is like this. The number is 890.4 kilojoules. It's one way to write this out. The other way to write it out is like this. Both of these mean the same thing. Now this time, this is exothermic because energy is on the right. So the delta H here is negative 890.4. This time it's negative because it's exothermic. Okay, now going back to the problem, which is in there on the top of that page. So what I'm going to do is I'm going to start with the 5.8 grams of CH4. So what I have is I have 5.8 grams of this, and we're trying to solve for delta H. So we're going here to the energy term. And so I'm going to do like we have done many times now, is I'm going to use the mole ratio. This time it's a very unusual ratio, 1 to negative 890.4, but that's what I'm going to do. So that again means the first thing I need to do is get this into moles. So the molar mass of methane is 16. Okay, and then I'm going to use the mole ratio. So 1 mole of this, negative 890.4 kilojoules. Okay, so if I do this on my calculator, 5.8 times negative 890.4 divided by 16 gives me this. It's a negative 322.77. And I come back to sig figs, and sig figs again are not determined by the conversion factors. They're determined by the starting point. So 2 sig figs, okay, and again, make sure I label it. So there would be the delta H for that problem. And this is what I'm talking about, using balanced equations, doing stoichiometry. Okay, and a lot of times, some of these other methods where delta H is involved, we do stoichiometry ends up being part of the problem. Okay, so now back to the notes. Okay, the next thing is what happens if we rearrange the equation. Okay, so rules for writing thermochemical equations. This is something we'll do throughout this chapter. But stoichiometric coefficients refer to the number of moles of each substance. If the coefficients are changed, delta H changes by the same factor. So here, the reaction I just did, in the first equation, in the second equation, I've doubled all the coefficients. So 2, 4, 2, 4. So what is delta H? So what we do there is we simply, like it says, if the coefficients are changed, delta H changes by the same factor. So if we double everything, we're going to double the delta H. So the delta H then, what will go in there, the delta H, if I double the delta H in that case, is negative 890.4, but I've doubled all the coefficients, so I'm going to just multiply by 2. And so what I get there, what goes in there is negative 1,780.8. So if you double the coefficients, you double the delta H. Oops, can't see that. This is what I did right here. So if I double the coefficients, I double the delta H. If I half the coefficients, I would half the delta H. Okay, and then when an equation is reversed, the sign of the delta H changes. So here is just the reverse of that first equation. So the delta H in this case, again, all I would do is change the sign. So the delta H there would be positive 890.4. So what goes in those for number 2 is, again, just change the sign, 890.4. And thermochemical equations are always specific to the state of matter. And I want to show you how these are going to add together. Thermochemical equations are always specific to matter, and I'm going to show you how these add up, which is kind of a glimpse into something that we are going to do later in this chapter. Okay, so let me write this out. So I've got, what I mean is this. So this, to me, it's a little bit like what we did. It's a whole different topic, thermochemistry versus oxidation reduction. But it's going to be using the same principles, just totaling the reaction. So if I take, I have H2O gas making H2O liquid. And the delta H is negative 44 kilojoules. Okay, and then we have CH4 plus 2O2 makes CO2. This is a gas. I should write this in. This is a gas. This is a gas. Makes 2H2O gas. And the delta H here is negative 802.4. Okay, now what we're trying to get to is this. Okay, we want to know the delta H for this. So what I'm going to do is I'm going to rearrange these equations. Again, this is something. See you, Lexi. Have a good weekend. Have a happy Halloween. And so if I look at this, the only thing that I need to change, so I have one CH4. So I want to total these two. I'm going to total these two reactions to this. So if I have something common on the left and the right, I'm going to cancel those out. So I've got CH4. I've got the two O2s. I've got CO2, but here I've got H2O liquid, and here I have two of them. I have two of them here, and I need two. So what I need to do then, if I want two, this is my target, this is what I'm trying to get to, then I needed to put two here and two here, and I'll show you how this works. But again, if we double the coefficients, we got to double the delta H. So if it's negative 44, I'm going to multiply that by 2, so it's going to become negative 88. Now if I total this up, if I have something common on the right and the left, I'll cancel that out. Well, that's what I have here, 2H2O gas on both sides. So I'll cancel that out and look at what I got. I got CH4 plus 2O2 plus CO2 and then 2H2O liquid. And the delta H value now is just to add those two up. And if I add those two up, what I get is negative 890%. Negative 890.4 kilojoules. So again, all I did then was I just added those up to get that. And again, this is something we're going to talk about. It's called Hess's Law that we're going to get to later in the chapter. But the concept there is how we change the coefficients, how the delta H changes with that. Okay. Okay, and then what it says here on the bottom, it says the enthalpy of a substance increases with temperature. Therefore, most reactions are expressed at a temperature of 25 degrees Celsius. And to be honest with you here, temperature is not going to be a factor in these problems at all. Okay, so there is number one. That's the first way that energy is involved in reactions, is just using stoichiometry and balancing around. The second way is calorimetry. We're going to talk about calorimeters, maybe not in today's lesson, probably the next one. But calorimetry, calorimeter is a measurement of the heat changes between a system and the surroundings based on the law of conservation of energy. So we're going to use something, and this is going to be review now from what we did in first year chem, specific heat. And you will be given a table, like it says here. Remember the units on specific heat. Joules over grams times degrees Celsius. So specific heat, lowercase s is defined as the amount of heat energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. But what we're going to add to that in AP chemistry is this thing called heat capacity. So first we're going to review Q SMAT, and then I'm going to show you SMAT plus CAT, and it'll involve this. So the amount of heat required to raise the temperature of an object by 1 degree Celsius. And notice the unit on that is joules per degree Celsius. Okay, so here is, again, review. And if you look on the formula sheet, and I'll point this out, they actually write it, they use C as the value. They call it MCAT, where I've always taught it and known it as MQ is equal to SMAT. Same thing. So you just need to see that off the formula sheet. The Q is energy, in typically joules, could be calories. M is mass. S is the specific heat. And then delta T is the change in the temperature. And it could be Celsius or Kelvin. I want to make sure the units line. Okay, so here's an example problem. So if we were sitting in class, I would have you guys do this problem. Okay, and hopefully that is not a difficult one for you guys to do. It's right from first year chem. But back on our formula sheet, so if you look on our formula sheet again, here's the front of the formula sheet. If you look on the back, and this is something that you guys might want to know, maybe it's on the front. Maybe it's on the back. Yeah, it's on the back. It's right here. I was right. It's on the back. So right here where it says, they're calling it MCAT. We've called it Q is equal to SMAT. But you'll see if you look up C over here on the right, they tell you that C is, it's the third one down, is the specific heat capacity. Okay, so if I do this problem, so Q, we'll just do it the way we've done it. It's the same thing. Again, on the formula sheet, it's MCAT, the same thing. So the specific heat capacity, and for water, they would give you this. This you'd have to be given. And that, if we do so many with water, you almost get it in your brain. And the mass of the water is 466 grams. And then the change in temperature is 74.6 minus 8.5. Okay, so if I do the math here, again, first of all, before I do the math, I want to do the units. So grams cancel out. Degrees Celsius cancel out. That's what this is. And that leaves me in joules. And this is what I had on my calculator. Okay, and sig figs, I think I should have 3 sig figs. So I'm going to use scientific notation. I could go like this. I guess I don't have to use scientific notation. Or I could do this. I think, am I right? I think I should have 3 sig figs. Okay, and that is probably a good place to stop. Let me just barely talk about the next slide, and that's where I'm going to pick up in our next lesson is the calorimeter. Okay, so whoops, way back to the start. We've already covered a lot of ground in this chapter. Okay, so now, again, we're still under calorimetry. We just talked about this. We just did this slide. And this is what we're going to pick up on the next lesson, the 2 different kinds of calorimeters, calorimeters. And That's a good place to stop. So guys, be studying, and I will talk to you soon.